And our first speaker this morning will be Sylvia Morrow from Holden College. She worked with me this summer and Rob Elder from Ohio Wesleyan on a nuclear physics project. We also had collaborators from Florida State University, Brazil, and Germany. And the title of her presentation today will be Searching for Rigid Triaxial Deformation in Germanium-70. So we'll turn the floor over to Sylvia. Get her set up. Oh, and real quick, we do have a fancy clicker. If you want to use it, the right arrow is an advance, the leftward pointing arrow is a reverse, and there is a laser also pointer at the top. So feel free to use that. Or if you want to use a green lightsaber, you can use it.
Hello. So today I'm going to be talking about searching for rigid triaxial deformation in Germanium-70. Just to give you a little background, according to the nuclear model, nucleons fill orbitals in discrete shells like this. So for Germanium-70, where we have 32 protons and 38 neutrons, protons would fill up to here at 32, and then neutrons would fill orbitals independently, so up to here at 38. You'll notice both of them lie right here in between the two magic numbers 28 and 50, and this is significant because magic numbers correspond to closed shells in nuclei. So many nuclei can be modeled as spheres, but there's also types of deformation that you see in nuclei, and the most common one is prolate. So this is like the shape of a football, and then there's also oblate, which is like the shape of a frisbee. And then the third is triaxial, and basically the criteria is that there's no symmetry axis. So if you were to take the symmetry axis of an oblate shape here and kind of pull it out that way so it's no longer symmetric, that would be an example of triaxial. So there's two types of collective motion that you see in a nucleus, and that's rotation and vibration. What I'm going to be focusing on today is called gamma vibration, which is basically vibration in this direction as opposed to this direction, which is beta vibration. So a nucleus, an isotope close to Germanium-70, Germanium-76, was recently found to exhibit rigid triaxial deformation at low spin. And just to explain this diagram here, we have energy on the y-axis. These horizontal lines are called energy levels, and then the arrows in between are called transitions, which are basically just gamma rays of particular energy. So say you have a nucleus populated to this 9- state, it will then want to relax to its ground state here, and it'll do that by emitting a cascade of gamma rays down one of these paths. So in Germanium-76, the gamma band here, gamma vibrational band, has been of particular interest because, as I said, it shows rigid triaxial deformation, which is extremely rare, not even just in this area, but all across the nuclear landscape. So I was looking at Germanium-70 and trying to see if I could find the same type of deformation at low spin also in Germanium-70. So I focused on here and here, because this looks like it could be a possible foundation for a gamma vibrational band in Germanium-70 because of these transitions to the ground state band and because of this base at the 2+ level. So for the summer, my goal was to extend this band to the point where I could make sure that it is a gamma vibrational band, and then I could do some analysis to see what the associated shape is. So the experiment I looked at is a oxygen-18 beam of 50 MeV impinging on a manganese-55 target. The fusion product is arsenic-73, and this then ejects light particles, and the most prominent product is germanium-70, which is when there's 1 proton and 2 neutrons ejected. So since this is a high energy reaction, the germanium-70 nucleus is then at high energy state, and it needs to relax to its ground state, and it does this by emitting a cascade of gamma rays. So the most important part of the apparatus to my analysis was the high purity germanium detector array. So here we have the oxygen 18 beam coming in from the accelerator. It hits the target, and then it's surrounded by 10 gamma detector arrays. There's 6 here, and then there's like 4 coming from the back and from the front. So more specifically, what I was looking at is what's called a coincidence experiment. And this is when a valid count or a valid coincidence count is when you see 2 gamma rays within a 100 nanosecond window of each other. So basically the way this works is, let's say you see a 4 keV gamma ray in this detector, and then in any of the other detectors, say this one, you see a 2 keV gamma ray within the 100 nanosecond window. It would be considered a coincidence count, and you would add a count to your matrix, your coincidence matrix. And the 100 nanosecond window isn't significant because on average, a new nucleus is produced in the reaction every 100 nanoseconds, and the amount of time taken for the nucleus to relax to its ground state is much smaller than this. So we can estimate that if we see 2 gamma rays within that window, they both come from the same nucleus or the same cascade. So the matrix fills up, and you end up with something like this. You can visualize this as kind of a 3D surface where the large numbers are like a peak and the small numbers are like a dip. And what I look at are gates or slices of the matrix. And then I focus on which gamma rays I saw most frequently in coincidence with other gamma rays. So that looks like something like this. This is a histogram of a 1068 keV gate. And basically what I did in my analysis is I would look at where peaks are in the gate. I would try and identify where they come from. Are they from a known germanium-70 transition? Are they from a different nucleus produced in the reaction or something like that? And then whenever I would see a peak somewhere where I couldn't figure out where it was coming from, especially if I saw it over and over, I would see if I could place it in the germanium-70 level scheme. So this is a partial level scheme for germanium-70. You see the 1068 here, that's what we're gating on. And then you also see all these other peaks down here below it that are in coincidence with the 1068. So as I said, my focus was to extend the gamma vibrational band for germanium-70, and that's what these red transitions are here. And then and one more important thing to notice is that there's these connecting bands to the ground state band. That's a good indication that this is a gamma vibrational band. And it's also a good indication that these extensions to the gamma vibrational band are in the correct place because we have 2 transitions coming from the new proposed state to known states. So for my analysis, I first looked at the static moment of inertia. And the important thing to notice here is this is germanium-70, and then here is germanium-72, the gamma vibrational band in germanium-72. And this steep slope is a good indication that this is a gamma vibrational band. I also looked at what's called a staggering parameter for germanium-70. Here we have germanium-70 in red, and then it's compared to other nearby even germanium isotopes. And the important thing to notice here is that germanium-70 is in phase with most of the nearby germanium isotopes, except for germanium-76, which, as I said earlier, has recently been shown to exhibit rigid triaxial deformation. And basically, what this indicates is that germanium-70 is actually more similar to other germanium isotopes, not germanium-76, so it's probably more gamma soft, which basically means that it doesn't show any particular preference toward the shape like prolate or oblate at low spin. So one last thing I looked at, it's called the total Ruthian surface. Basically what this is we have a contour plot here of potential energy. The dot is the point of lowest potential energy, and then the polar coordinates show degree of deformation in the radial direction and type of deformation in the angular direction. So here, this is a plot for the ground state band for germanium-70 at the lowest spin state. And what's important to notice here is while we have a dot here kind of near oblate, we have this really wide region of low potential energy. And basically what that is a good indication that germanium-70 is gamma soft, meaning it does not show a strong preference towards a particular shape. You could kind of go anywhere here at low spin. And then just for comparison, this is germanium-70, the ground state band, but at higher spin. And you'll see the dot is in a much smaller area of low potential energy, and here it's more prolate. So that shows sort of a more rigid structure, more preferential towards a specific shape. Any questions?
Okay, this talk is open for questions and discussion.
Right, Sylvia, could you show the static moment of inertia plot again? Just wonder if you could help me understand what I'm supposed to take away from that.
Yeah.
graph.
So here we have germanium-72. This is the even side of the gamma vibrational band. And then this is germanium-70, the even side of the gamma vibrational band. And basically, it's been shown theoretically that if you see a steep slope for this, it's a good indication that it is gamma vibrational band.
So it's basically the quantum mechanical analog of the classic moment of inertia, right? But quantized, sort of a local moment of inertia as the rotational frequency changes of the nucleus. Other questions or discussion? Okay, let's thank our speaker again.